For section 6.2, we're going to look at the trig functions, but from a right triangle perspective. And so here we have the definitions of the sine, cosine, tangent, cosecant, secant, and cosecant, but all based on a right triangle instead of the unit circle. So our right triangle, again, is a triangle where we have a 90-degree angle on one corner, and then we have three different sides that we label as the hypotenuse, the adjacent, and the opposite. The hypotenuse is the longest side. The opposite side sits across from the angle that we label as theta, and the adjacent sits right next to the angle theta. And then we define the different trig functions this way using the lengths of the sides in the right triangle. The sine theta is defined as opposite over hypotenuse. Cosine of theta is defined as adjacent over hypotenuse. Tangent is opposite over adjacent. Cosecant is hypotenuse over opposite, which again is just the reciprocal of sine. Secant is hypotenuse over adjacent, reciprocal of cosine. And cotangent is adjacent over opposite, reciprocal of tangent. So these give us a handy way of solving and working with angles and lengths of sides in right triangles. And so first off, one thing that people like to use to help remember what each of these are for the ones we use the most, sine, cosine, and tangent are most of the commonly used functions here. But the acronym SOHCAHTOA is often used to help remember what sine and what cosine and what tangent are. So for instance, the first one would be sine. The O and the H stand for opposite, hypotenuse. The CAH stands for cosine. And the A and the H, that's adjacent, hypotenuse. And then the TOA part is for the tangent. And that would be opposite over adjacent. So just in case that helps, remember some of the different sides in the right triangles that we use for the sine, the cosine, and the tangent. All right, for a few examples here, let's start off with our right triangle trig. For example 1, I'm going to be looking at this triangle and figuring out what the trig values are from there. So notice how they put the theta here on this angle. We can identify any angle as theta, but this is just the one we're using for now. And we know what the measures of the other sides are here, all three sides. So we need to know what is opposite, what is adjacent, and what is hypotenuse. Well, the longer side and the side across away from the right angle, that would be the hypotenuse. The side next to the angle, that would be the side adjacent. And the other one would be the side opposite. And so what we're going to do here is we're going to write out the values starting with the sine of theta. Sine of theta would be opposite 2 over hypotenuse 3, so 2/3. The cosine of theta would be the adjacent square root of 5 divided by the hypotenuse 3. The tangent of theta is the opposite 2 over the adjacent square root of 5. So this is the values here, but oftentimes we'll rationalize the denominator when it's a square root, such as this one. So I'll multiply by square root 5 top and bottom to change this into 2 square roots of 5 over 5. Would be the way it's more commonly written. Now the secant of theta, well basically we can just take the cosine and flip it around, so that would be 3 over the square root of 5. Another situation where I need to rationalize. So it'll be turned into 3 square roots of 5 over 5. The cosecant is the reciprocal of sine, so if we do that, we'd have 3 over 2. And then finally, the cotangent. We could flip around the tangent to do 5, or square root of 5 over 2. And that would be our cotangent. And so these are the values of all 6 trig functions based off of this right triangle. Now for example 2, it says cosine alpha is equal to 3 over 4. We want to sketch a right triangle with the acute angle alpha and find the other 5 trigonometric ratios for alpha. Okay, the only reason they're using this different symbol is just to show that different symbols can be used. We're generally lately been using theta, but alpha can also be used as a symbol standing for an angle. So a right triangle would look something like this. What I want to do is figure out all the other trig values from here. But all I know is that the cosine of alpha is equal to 3 over 4. So what does that tell me about the sides in this right triangle? Well, in this case, 3 would be the adjacent, and 4 would be the hypotenuse, since cosine is adjacent over hypotenuse. And so I'll label the sides here with those numbers. Again, the adjacent would be down here, the opposite would be over here, and this side would be the hypotenuse. So the adjacent is 3, and the hypotenuse is 4. We don't know what the length of the side opposite is, but we can solve for it. So what I'm going to do is going to solve for the opposite side. The way we can do that is through something called a squared plus b squared equals c squared, which is a special equation that works on right triangles, which is called Pythagorean theorem. And so if we plug in the lengths of the a and the b stand for the side, the smaller of the two sides, and the side c stands for the hypotenuse side. So if I plug in here for a, 3 squared plus b squared equals 4 squared. So 9 plus b squared equals 16. Subtract the 9 over, b squared equals 7. We'll take the square root. Generally, put a plus or minus here. So b would be plus or minus square root of 7. However, since we're just using the sides of a triangle, we're not worried about the negative value. And so what that tells me is the length of the side opposite is the square root of 7. And so what we can do from here is we can figure out that the sine of alpha will be opposite square root 7 divided by hypotenuse 4. The tangent alpha would be the opposite square root of 7 over the adjacent 3. The cosecant of alpha would be 4 over the square root of 7, which when we rationalize it would be 4 square roots of 7 over 7. The secant of alpha, that's the reciprocal of cosine, so that one would be 4 over 3. And then finally, the cotangent alpha, reciprocal of tangent, would look something like 3 over the square root of 7. When rationalized would be 3 square roots of 7 over 7. So for this example, we're looking at a triangle where we only know 2 pieces of information, the length of one side and one of the angles. And so we're going to be able to use our trig functions in a right triangle in order to solve for the missing pieces. So for the 2 missing sides is what we're going to be really trying to get to here. Okay, and so how we're going to approach this is we need to know which side's which. The long side is the hypotenuse, and then we have the side opposite, and we have the side adjacent. And so let's start out by trying to find side A. To find the side A, I need to identify which trig function would be appropriate here. In this case, I have the hypotenuse, and I'm going to be looking at the opposite with that. So what we're going to use is the sine of theta, which is again opposite over hypotenuse. So what that means is we say sine of 30 degrees is equal to the opposite, which is the letter A, divided by the hypotenuse, which is 12. And so solve this. I'm going to multiply both sides by 12, like so. That way it solves this and says A is equal to 12 sine 30 degrees. Now there are ways of calculating this by hand, but for now let's use a calculator so we get adjusted to calculating these with the degrees. And so I want to calculate 12 sine of 30 degrees. One thing I need to do in order to calculate this though is I need to make sure the calculator is in degree mode. So back in section 5.2 I mentioned about radian versus degree mode. Now we've talked about both radians in the last section and now degrees as well. And so we'll be able to switch our calculator between these two different modes depending on what kind of angle we're using here. So now we're using degrees. So let's switch our calculator into degree mode. If I don't do this, it's not going to calculate it in the right way. So now in degree mode, if I put in 12 sine of 30 degrees, it's going to calculate it for me and tell me that it's equal to 6. So A is equal to 6. Side opposite is equal to 6. Now, to find the other side, B, on the adjacent, we technically have two options at our disposal. We could use a squared plus b squared equals c squared, since we now have two of the three sides. But just as an example, I'm going to go ahead and use the cosine of theta, because the cosine of theta is adjacent over hypotenuse. So what that would look like for this triangle is cosine 30 degrees is equal to adjacent b over hypotenuse 12. So what I'll do here, multiply again both sides by 12. And so we'll get b is equal to 12 cosine of 30 degrees. Now if I use the calculator here and plug that in degree mode, it's going to tell me this much. So I'm going to round that to the nearest tenth. So I'm going to round that to 10.4. So B is approximately 10.4. So now we have two sides of the right triangle figured out. All three sides are known. The only thing that's actually still missing in this triangle is the angle B up here at the top. So let's figure out how we might find a missing angle if necessary. To find angle B, what I'm going to do is use the fact that there's 180 degrees total in any triangle. And if I subtract away the angles that are known, which we know 30 degrees, and since it's a right triangle, 90 degrees, what's left over is 60 degrees. And so that would tell us what angle B is here. So now we have everything good to go. We have our side opposite, which is equal to 6, our side adjacent, which is approximately 10.4, and we've solved for all the missing pieces. Now there's two particular kinds of angles we need to address and the vocabulary they use for them, called the angle of elevation and depression. And this is basically coming from how the angles are measured. If we start with measuring the angle upward from some flat surface like so, we call that the angle of elevation. However, if we start from a flat surface or a flat point of view forward, horizontal, and measure it downward to something, then that angle would be called the angle of depression. And so we're going to look at some examples here, starting off with example 4. It says a giant redwood tree cast a 532-foot long shadow. Find the height of the tree if the angle of elevation to the sun is 25.7 degrees. Okay, so let's construct what's going on here. We're going to consider the ground as level in this particular situation. And then we have a tree here. We're measuring at the end of the shadow the angle of elevation to the top of the tree. So the sun is up here, casting its shadow downward. And so the angle of elevation will be the angle from the flat ground upward, and that's the 25.7 degrees. And we know the length of the shadow along the ground is 532 feet long. We'd like to find the height of the tree. So what I'm going to do is give it the letter H for the height, and then start thinking about how this right triangle is constructed. So we're going to consider the right triangle here. So with our angle in the position it is, this would be the side opposite, and this would be the side adjacent. So we have to think about which trig function uses the opposite and adjacent. Technically there's two, but the one we're going to use pretty much all the time is tangent. Tangent theta is equal to opposite over adjacent. And so in our case, we plug the numbers in, or the letters and so forth. We get tangent 25.7 degrees is equal to opposite h over adjacent 532. So we'll solve this for h. I'm going to multiply both sides by 532. That way that number goes away. So we're going to have your h is equal to 532 tan 25.7 degrees. And just to illustrate this one more time in the calculator, if we plug it in, 532 tan 25.7, again with degree mode, we get this much. We're just going to round that off to the nearest foot in this situation. So we're going to say that h is approximately 256 feet. Now for example 5, it says from a point on the ground 500 feet from the base of the building, an observer finds that the angle of elevation to the top of the building is 24 degrees, and the angle of elevation to the top of a flagpole on top of the building is 27 degrees. Find the height of the building and the height of the flagpole. So let's illustrate this here. This will be my building, and then there's a flagpole up here at the top of that. Okay, and then from a point 500 feet from the base of the building, we measure the angle of elevation up to the top of the building and get 24 degrees. And then we measure the angle of elevation up to the top of the flagpole, and that's 27 degrees. So what I'm going to do here, starting off with the height of the building here, call that h. And then we'll look at the building and the flagpole together, and we'll call that k. So the first thing I'm going to do here is I'm going to find h. Now the sides of the triangle we're dealing with here are, on this side would be opposite, and this side down here would be adjacent. So we're going to go back to using the tangent. Tangent of 24 degrees is equal to opposite h divided by adjacent 500. And when we solve for h here, we'll get 500 tan 24 degrees. And when running that in the calculator, it turns into approximately 223 feet. So just the building itself is 223 feet. Now to find K, we basically do the same thing. But we're going to use 27 degrees is equal to K over 500 with the tangent. So K would be equal to 500 tan 27 degrees, which will be approximately 255 feet. So that's both the flagpole and the building all at the same time. So if we want to know just what the flagpole would be as its height, we take the 225 feet minus the 223 feet from the building to give us 32 feet for just the flagpole alone. For example 6, we have another scenario. It says a plane is flying within sight of the Gateway Arch in St. Louis, Missouri at an elevation of 35,000 feet. The pilot would like to estimate her distance from the Gateway Arch. She finds the angle of depression to a point on the ground below the arch is 22 degrees. What is the distance between the plane and the arch? Okay, so to illustrate this, we think of the plane as just flying straight horizontal. Makes things easy. But we're measuring the angle of depression downward to this location on the ground. Okay, and so that angle of depression downward is 22 degrees. So what we'll do here is construct a right triangle from this information. We'll just kind of consider the ground as level in this place, so we can make a right triangle out of it. And what I like to do is consider the fact that I have 90 degrees here with the perpendicular line that drops down straight to the ground. There's 90 degrees there, and the horizontal direction the plane is traveling. So we can figure out this angle that's inside of our right triangle by taking the 22 degrees and subtracting it away from 90, which gives me 68 degrees. Okay, and now we also know that the elevation of the plane is 35,000 feet. So that's the length of that side of the triangle going straight down to the ground. And so we want to know what's the straight distance from the plane to the arch. So I'm going to call the side that has that distance L, or length. And now let's label the sides of our triangle. This side with the 35,000 would technically be called the side adjacent, since it's right next to the 68 degrees here. So that's our side adjacent. And then this would be the hypotenuse for the side that I've labeled as L. And so the question is, which trig function do we use with adjacent and hypotenuse? That would be the cosine. Cosine is adjacent over hypotenuse. So in this case, it would go cosine of 68 degrees equals the adjacent 35,000 divided by the hypotenuse L. Now I have to solve for L somehow. I'm going to multiply both sides by L, and that would make it look like L cosine 68 degrees equals 35,000. Now what I'm going to do is I'm going to divide both sides by cosine 68 degrees. And so L is going to equal to 35,000 divided by cosine 68 degrees. Now I have to put that in the calculator and get an approximation for it. And when I did, I got approximately 93,431 when rounded to the nearest foot.